Okay, let's get started with today's experiment run through. Today we're going to be looking at experiment 4, calorimetry, temperature, and specific heat. This is a very interesting laboratory in that it can be done with simple equipment, and we'll be showcasing some examples of various calorimetry experiments and various calorimetry techniques. First and foremost, let's talk about where to find this lab. This is found in the Chapter 5 laboratory module. So first and foremost, we're going to find the experiment 4 temperature and specific heat page. This looks like the following page. So this is going to contain all of the recordings and experimental data that we'll be using in order to create a full lab report and fill in our lab report sheets. We also have the lab submission page. This is where you're gonna be submitting your final report. And finally, we also have a set of pre-lab lecture recordings, which provide some background information on the laboratory and how to complete the experiment. So now that we know where everything is and where to find everything in the modules, again, this is the lab page, this is the pre-lab lecture, and this is the report submission page. We're going to open up now the experiment 4 lab page. If you haven't already, please engage with the pre-lab reading found not only in the lab page introduction section, but also in the recommended reading. As noted in the required reading, we have to look at the experiment 4 lab manual pages. So I'm going to pull up the lab manual. So here's experiment 4. This is the full lab in your lab manual. And what we're going to do is I would encourage you on your own time to read through the introduction section because it contains a lot of very useful information that you will have to reference. Additionally, as we continue scrolling through this set of lab pages, we're now going to get to the experimental procedure, which we'll come back to in a moment. And finally, we have the pre-lab questions that you'll be answering before starting the lab. And now we have the report sheet. As convention, I've taken the liberty of placing the report sheets into my drawing tool so we can fill them in as we work through this experiment. Now, continuing on, let's now pull up our experiment procedure and let's go in the lab page and let's find our experimental procedure. Okay, so here's our experimental procedure. Allow me one moment to adjust the margins slightly. There we go. Okay, so let's find our experimental procedure. So here we go. We have the experimental procedure for part A. So let's read what we're doing for part A. So in this case, we're using a thermometer. We're using a beaker with some ice, water, and salt. Okay, we're going to observe our thermometer. In this case, we're using a digital thermometer rather than a graduated thermometer, just due to the fact that it updates a little bit more quickly and it's a little bit easier to take fast readings from the digital thermometer. We're going to look at a beaker filled a third with water and record its temperature. We're going to have a beaker with ice water and we're going to record its temperature. And then we're going to have a beaker with ice water containing salt. And salt in general, when you add solute to a solution, it lowers the effective freezing point. So if you add salt to ice water, what you'll notice is that the temperature of the ice water is going to be typically lower than that of pure ice water. This is the same reason why if it's ever snowing, they put salt on the roads, as it helps facilitate melting off the ice. Okay, so now that we have our instructions, let's view some photos. So we have the temperature of room temperature water, which is about 23.4 degrees Celsius. So let's just write that down. You'll be responsible for converting these temperatures to Fahrenheit and Kelvin. The temperature of ice water, as we notice, is markedly lower, about 0.4 degrees Celsius. Finally, the temperature of ice water and salt is about negative 4.1 degrees Celsius. So if you were to prepare a cooler to take on like a camping trip or something, you'd probably want to use salted ice water rather than just normal ice water. You do have to add a fair amount of salt for this effect to be observed, but nonetheless, we can see that there's a substantial difference in temperature between the ice water mixture and the ice water mixture containing salt. After completing this section, you're going to answer these two questions. And now we're going to move on to talk a little bit about specific heat. So for specific heat, I prepared a full video recording with narration where I measure the specific heat. I'm going to be explaining what's happening in the video recording and explaining what data we're going to collect. So let's read the protocol first. So in a broad perspective, we're going to obtain a piece of metal. We're going to weigh that piece of metal. That piece of metal is then going to be set aside for now, and we're going to take a styrofoam cup. We're going to weigh it. We're going to add about 50 milliliters of water to the cup, which is our calorimeter, and we're going to record the total mass of water and the calorimeter, and we'll use that to calculate the mass of water. From here, we're going to boil water and make a boiling water bath, and we're going to drop and place the metal object into the boiling water bath. The metal object will reach the same temperature as the boiling water bath, and then we're going to transfer that heated metal object into our calorimeter. It will exchange heat with the water, and we're going to record the temperature over time. Once we find the maximum observed temperature, we're going to write that down inside our calorimeter. Based on the change in temperature in our calorimeter and the change in temperature for our metal, we are going to be able to deduce the specific heat of this metal and in turn deduce the identity of the metal. So that is the overview. Let's now view the recording. I'm going to expand this out a little bit just so that way we can see what's happening. So here I have a metal piece, and that metal piece, it looks like aluminum to me, and it is in fact aluminum, and we'll prove that via the specific heat measurement. So I have a balance set up. The beautiful thing about this lab is that this is a classic lab that can be done as part of home chemistry experiments. You're not going to be actually doing this lab at home, but I'm providing a recording to show really how accessible this kind of experimental protocol is. Calorimetry requires very simple equipment, but is quite powerful. Okay, so we see first and foremost that we are recording the mass of the metal piece. So this is 9.9 grams. So let's write that down. The mass of the metal piece is going to be the same for both trials. For the identification number, you can just leave this blank or you can put 0. We're only using one piece of metal. If we were doing this lab face to face, we would be having multiple different metals, each with their own numbers on them. But because we're all using the same data set, we're just going to keep the identification number blank for now. Okay, let's keep going now. And I strongly encourage you to watch this full video with narration on. I don't have the narration on for the original video right now because we're working on this virtual lab together and I'm explaining some things regarding how to complete the lab. But if you watch the video, I talk a lot about the experimental protocol and procedure and why I'm doing each step. Okay, so I finished weighing out the metal piece. And now We're getting our coffee cup calorimeter, which is essentially just two styrofoam cups. The reason why we use two styrofoam cups is to provide insulation from the outside environment. So I have my coffee cup calorimeter assembled, and now I'm going to place it onto the balance. I'm also going to put all the cap and other things on. And what I've done here is I've tared it. So let's pause here. The reason why I decided to tare the calorimeter is because I really am only interested in the mass of water. So a tear tells the balance to subtract the mass of the calorimeter from any future weighing instances. So let's record that. So we'll just put 0.0 grams, and we're just going to note that it was tared. If you were taking these measurements in an actual lab where multiple students are using the same balance, the reason why you write down the mass of the calorimeter and you don't just tare it is because if multiple people have their own calorimeter, they can very easily reset the tare. But for here, we're very much interested in just the mass of water. And because I have my own personal balance that I'm using in this recording, I can just hit the tare button and continue on. We're going to be doing this run through together for one trial, and I'm going to expect that you watch the remainder of this recording and collect data for your remaining trials. I do a total of 3 trials. You only need to record the data for 2. So we'll do one together. So I am setting up and taking some water, and I have dispensed about 50 milliliters of distilled deionized water. You can buy deionized water, so it's not it's not an inaccessible commodity by any stretch. And now I'm loading the water into my coffee cup calorimeter. Okay, now we're ready to take a mass measurement. So let's pause here. 48.3 grams. Let's write that down. Okay, now we have our calorimeter set up. And now we're ready to begin the most interesting part of this lab, which is getting the metal piece set up and at the boiling water temperature. The way this is done is quite simple. We're going to boil some water and we're going to load our metal piece into the boiling water for about 5 to 10 minutes. So I'm getting my thermometer ready. I'm setting up my calorimeter so that it's ready for transport. And again, the layers of air provide a separation, just like a thermos. So I have my calorimeter with a thermometer in it. And now we're going to get ready for the next step, which is the heating step. So here's my metal piece that I'm carrying along with me. And now here's the cut to when we're ready for heating. So I'm going to boil up some water. I've boiled some water. I have my coffee cup calorimeter ready to go. I've loaded and I'm going to load the metal piece into the boiling water. And we're giving this some time because it takes a little bit of time for the metal piece to heat up. I have an oven mitt to help with handling the heating setup, and I have some tongs ready to go. So I'm going to load the metal piece. into the boiling water. Now we're going to wait a little bit as the temperature has to equilibrate. In the meantime, what we're going to do is we're going to take an initial temperature reading for the water inside our calorimeter. So before anything is added to the calorimeter, let's record that temperature of the water inside the calorimeter. So this initial temperature is 21.6 degrees Celsius. Okay, makes sense, around room temperature. Now we're going to record the temperature of our boiling water bath. And to this end, we'll address the boiling water bath in a second. We're now transferring the metal piece into our calorimeter. So I have the metal piece that I have brought to the temperature, and I'm quickly going to drop it inside the calorimeter, make sure it's fully immersed, and then I'm going to immediately put the cap on. This temperature exchange is not going to be instantaneous. This isn't a, we're not perfectly accounting for heat loss to the surroundings. But nonetheless, we can record the temperature of the water after it's been brought in contact with the metal piece. As we can expect intuitively, the temperature is going to increase. And we're going to monitor that temperature increase over time. And eventually, what we're going to find is we're going to hit a maximum temperature. So as you notice, the temperature has increased. Now it's about 23.3. We're not going to write this down as like our final temperature reading because there's still some time for heat exchange to occur. So as time passes, the video has been edited such that we're going to allow some time to pass, and then we're going to take an additional reading. So 23.3 once again. And 23.3 once again. So again, we're just allowing heat exchange to occur, and we're continuing to record the temperature. Okay, so let's write the final temperature. As you can see, the temperature increased by about 1 to 2 degrees Celsius, about 1.5 degrees Celsius of temperature increase, which is pretty significant considering water has an appreciable specific heat capacity. Okay, so as you can see, we recorded our 2 required temperatures. Now, as promised, we're going to record the temperature of the water bath. So after a little bit more time has passed, let's make an adjustment to our temperature reading because the heat transfer wasn't quite finished. It actually jumped to around 23.5 degrees Celsius. So we'll make that correction. Again, you really have to make sure to watch the video fully just to make sure that the final temperature is actually the final temperature because this heat exchange takes a little bit of time. Okay. Now we have the second trial set up, which we're going to be showcasing. I'm going to skip past this whole second trial setup because we're going to need to collect one last piece of data. when you're doing this lab on your own, you're going to watch and collect all this data for at least the second trial, since you have to get data for 2 trials. I've now panned over to the boiling water bath, and I took one temperature reading for the boiling water bath because I had the boiling water bath going for all of these trials. As you can see, the thermometer is beginning to equilibrate, and we're going to wait for the thermometer to settle at a temperature, and we're going to write down the temperature of the boiling water bath, which is the same as the temperature of the metal piece that we put in the boiling water bath. So we'll allow some time for it to equilibrate. As you see, the thermometer is continuing to increase, increase, increase. And now the temperature is steady at about 97.1 degrees Celsius. The metal piece is the same for the second trial, but you're going to need to watch the video and write down the mass data for the second trial, as well as the initial and final temperature. So now that we have this data set, you'll watch the rest of this video independently to collect the remainder of this data set. And now we can perform some calculations. First and foremost, for the delta T, all we have to do is take the difference between these temperatures. So if we have 23.5 degrees Celsius minus 21.6 degrees Celsius, that gives us 1.9 degrees Celsius. Okay. From here now, the mass of water, we have it as 48.3 grams. For heat, Q water is equal to the mass of water times the specific heat of water, which is 4.184 joule per gram degree Celsius, times delta T. We can substitute now. The mass of water we know is 48.3 grams, which makes sense. We dispensed about 50 milliliters. And the delta T is about 1.9 degrees Celsius. So you'll punch that into the calculator, and that will give you the heat gained by the water. The heat lost by the metal is the same as the heat gained by the water. So we'll just take whatever we get here and we'll plug it in for the heat lost by the metal. In terms of the delta T metal, we're going to take the final temperature, which is the shared temperature of the metal and water, which is about 23.5 degrees Celsius, and subtract out the initial temperature of the boiling water bath. We're going to treat this as an absolute value because of the way the lab manual set up the calculation. So 97.1 minus 23.5. Okay. That gives us 73.6 degrees Celsius. Finally, for the specific heat of the metal, the specific heat of the metal is defined as the Q metal, which we get from up here, divided by the mass of the metal times delta T. So in this case, we'll take the Q metal, which we got from up here, divided by the mass of the metal, which is 48.3 grams, times the delta T, which is 73.6 degrees Celsius. Remember, both the mass and delta T are in the denominator. So you're taking the heat of the metal divided by 48.3, and then you're going to take that result and then divide it by 73.6 degrees Celsius. So that's an overview of how you complete this laboratory. Just to give you some ballpark values for the heat of the water, if you were to punch this into your calculator, you'd get about 400 joules, give or take. And so just doing a back of the envelope calculation, 400 joules over 48.3 grams times 70 degrees Celsius. That in turn gives us about 1.7 joule per gram degree Celsius. I want you to input these calculations into your calculator and report more exact numbers using the data set that we've collected. Just as a ballpark, your specific heat value should be between 1 and 7 joule per gram degree Celsius. If you're getting very large or very small numbers, that's a sign that likely you made an error in one step of the calculation. Okay, so we completed the specific heat section. Now we're going to answer the questions. In terms of identifying the metal, let me show you that. The lab manual has a table of different metals with their specific heats, and you're going to use the specific heat values that you measure in order to assign the identity of the metal. Now, the specific heat may not perfectly match. That's okay. You just want to assign the metal that's closest to your recorded data. Okay, let's move on to part C now. So in this case, this is a demonstration where we're going to measure the amount of energy in a specific food sample. When we consume food, we can convert it to energy, which can be used for other purposes. We're just going to burn the food sample. And what's happening in this process is by breaking some bonds and forming new chemical bonds that will release energy in the form of heat, and we can record that amount of heat released as our food sample is burned. So to this end, we're going to record the type of food. We're going to weigh an aluminum can. We're going to pour about 100 milliliters of water and weigh the can and water together. And now we're going to weigh our food sample. We're going to measure the temperature of the water before we burn the food sample. We're going to burn the food sample, measure the temperature of the water as we burn the food sample, and then we're going to weigh the remaining food sample to figure out how much food sample did we actually burn. Okay, so let's do just that. So here is the demonstration. Let me mute that just so it's not creating two different sets of audio. So here's the setup. As you can see, there's the food sample, a aluminum can, and some water. So first and foremost, they've taken the food sample and loaded it onto a display. So we're going to take this mass in its entirety as 10.0 grams. So the food sample, it looks like a peanut or other nut. The mass of food initially, we're going to have 10.0 grams. Because they have the food sample on this stand, after it burns, you're going to be left with a small amount of food sample remaining. And this difference between the final and initial mass is the mass of the food that we burned. Okay, so we can keep going with this. So they weighed the food sample. Now let's weigh the water. So they teared the setup. So, never mind. One moment. So this is just the empty can of 30.8. So let's write that down. So they have the empty can, and now they're going to transfer some water into it. So here's the water. The water gets poured into the can, and now we're going to weigh the can and water together, and we can determine the mass of water via difference. Okay, so our combined mass is 82.3 grams. So we have about 50 milliliters of water in there, give or take, about 50 grams of water, give or take. Okay, so now let's get to the exciting part. So we now have our food sample. We have the aluminum can that we have loaded into a setup that makes it easy to have it suspended. A temperature probe is being loaded into the water. And now we're going to be able to record the temperature of the water in real time using a sensing program. This is another example of a digital thermometer. So as we can see, 21.2 is our initial water temperature. 21.2 degrees Celsius. Okay. And I would encourage you when you watch these videos independently to have the audio on as they have some useful narration. Okay. Everything is being now set up. And now for the exciting part, we're going to take the food sample and it's going to be burned. As the food sample burns, it will generate heat, and that heat will get transferred into our water so we can record the temperature change of the water and get a sense of how much energy was released by our food sample. So as you can see, the food sample is starting to ignite. And now we're going to place that food sample under our water sample. So as heat gets transferred into the water, as the food sample burns, you're going to see that the temperature is going to begin to increase, increase, increase. Notice the temperature has increased a few degrees Celsius during this burning process. So the food sample is being adjusted to allow it to combust as much as possible. And we have our final temperature after the food sample has finished combusting. So that gives us a final temperature of 39.8. In terms of the mass of food sample remaining, as we can see, there's still a fair amount of food sample that has not ignited. So we're going to record the mass of the remaining food sample. So we get a mass of 9.7 grams. Okay, so we have all the data that we need for our calculations. For the mass of water, we just take the mass of the can plus water minus the mass of the empty can, which in turn gives us 51.5 grams. The temperature change for the water is just the difference between our final and initial temperatures. So we have 39.8 degrees Celsius minus 21.2 degrees Celsius. That gives us 18.6 degrees Celsius. For the heat gained by the water, let's do that. So Q water is the mass of water times the specific heat of water, which is 4.184 joule per gram degrees Celsius, times the change in temperature. So we have 51.5 grams times 4.184 joule per gram degrees Celsius times 18.6 degrees Celsius. And you're going to enter this into your calculator just to give you a ballpark value. So we have about 200 times 20. This is about 4,000 joules, give or take. The Q water is equal to the Q of the food sample. Even though the lab manual wants it in cals, you can do all of these calculations in joules, and that's more than acceptable. Joules are more common for calorimetry measurements. If you wanted to do these calculations in calories, all you would do is just replace the specific heat with the specific heat in calories, which is 1 cal per gram degrees Celsius, which in turn gives us about 1,000 cals. Lowercase. This is equivalent to 1 kilocal. Okay. So Q water is Q food. So these two values are equivalent. Any heat gained by the water was produced by burning the food sample. In terms of the mass of food that we burned, we took an initial mass of 10.0 grams. We ended with a final mass of 9.7 grams, and that leaves us with 0.3 grams. So then if we want the energy value, we'll take our kilocalories, which is about 1 kilocalorie, divided by 0.3 grams, which is about 3 kilocal per gram. You will go through and perform these calculations with a calculator and report more exact values so you can practice these calculations. I just wanted to give you some ballpark values so that way you can check to make sure your calculated values are not too large or too small and that your calculations were entered correctly. Okay, we completed this part and you'll answer the questions. Let's move on to part D. So for part D, we're going to obtain a food product. We're going to look at the label. We're going to record the serving size, and we're going to list the grams of carbohydrate, fat, and protein. From the mass of each food type, you'll calculate the calories for each food type in one serving using the accepted energy values. You'll determine the total kcals in one serving and compare it to the label. Now, it's important to note that carbohydrates are 4 kcal per gram, fats are 9 kcal per gram, and proteins are 4 kcal per gram. This is the set of energy values for different food types that was provided by the lab manual, and this is what we're going to be using for our calculations. So I'm just going to copy this and just make sure that this is available as I do these calculations. So let's look at our food sample. In this case, we have a sample of beans and we have the nutrition label. So the serving size is half a cup, 130 grams. So let's record the mass of different food types. Fat is 0, Carbohydrates is 21 grams and protein is 7 grams. Okay, so for carbohydrate, we have 21 grams times 4 kcal per gram. So this gives us 84 kcals. For fat, it's just 0 because there's no fat content. And then for protein, we have 7 grams times 4 kcal per gram, which gives us 28 kcal per gram. Adding this up, we get 112 kcal per serving. And let's see how that compares. The calories are 110 on the label. So we performed this calculation pretty accurately, I would say. So we finished part D. You'll answer the questions, and then you'll submit your entire report, all of your completed report sheets in the experiment for calorimetry and specific heat page. So that concludes our lab run through.